All right, so we'll take a look at some of the examples from the current module topics, which looks at organic compounds. So we'll take a look at the first one here, which is drawing some of the structures, the Lewis structures for fairly simple organic compounds. So these are not going to be really big. They're going to be made up of maybe 4 or 5 different atoms. But you want to use the same principles that we learned earlier on when we were drawing Lewis structures. So typically when you're given the formula, what I like to do is to have a piece of paper close by and actually draw the structure separately, and then you can transfer it over to the ALEKS template. So if I have C2H4, remember you want to pay attention to the octet rule. That's going to be our guiding principle. Carbon, remember, likes to form 4 bonds. Hydrogen is an exception to the octet. It can only form 1 bond. And as a general rule, when you see carbon in a formula, you want to stick that in the middle, right? And we saw several examples of that earlier on. So if I have 2 carbons, I'm going to connect those in the middle, and then I have 4 H's. So let's think about where those H's can go. The H's cannot go in the middle. They're going to have to go on the outside. And that means we can attach them like this. So if we look now, we can see that our hydrogens each have their 1 bond. Carbon, this carbon here on the left has 1, 2, 3. The carbon on the right has 1, 2, 3. So each of them needs an additional bond, and we can solve that problem by introducing a double bond between both of the carbons. So when I draw my structure, I need a carbon. So I click on the adding an atom, and I just type in carbon. I need a bond. I click on the add a bond tool. I need another carbon right here. So I click on add an atom, type in C, and I'm going to draw in my additional bond. So I need 2 single bonds. So 2 of those, and those are going to be to my hydrogens. And on the other carbon, I need 2 bonds as well. I'm going to attach some H's onto those. So I click add an atom, type in H, click add another one, H down here at the bottom, add another one over here, and another one on the left side. And I need my double bond. To introduce a double bond, I'm just going to hover over that single, and I click on it again, and there I have my double bond. I'm going to check, and it looks correct. Now, the other thing that you want to make sure that you include, and it's shown here, you want to make sure that you include any lone pairs. So in the case of hydrogens, we don't need any lone pairs because remember the hydrogens only need 2 electrons, and we already have those. The carbon has 2, 4, 6, 8, so there aren't any additional lone pairs. But in some cases, you will need to draw those lone pairs in, and you would click on the add the lone pair button here at the top to introduce lone pairs. So for example, let me try another one. If I wanted to, I'm just going to draw in, let's say a BR. If I want to draw some lone pairs on that, I'm going to click on add a lone pair. And I'm going to put my first. Now, when you put your second, right, remember the lone pairs go in, you wouldn't want to put it like that because you have 2 lone pairs on the top. You need to put them in separately. All right. And by that, I mean, if I have a BR, I put 1 lone pair on the top, 1 on the right, 1 on the bottom, like that, for instance, right? And this is something we've seen previously. All right, so the next one, we're going to identify, for given our structure, some of the hydrophobic and the hydrophilic parts of an organic molecule. So generally, when you look at organic compounds, because they're made up mostly of carbons and H's and bonds between them, they tend to be mostly non-polar, but sometimes you'll have atoms that are different, and depending on their electronegativities, they're going to be you're going to introduce some sort of polarity into the molecule. So as a quick reminder, hydrophobic means water hating, And this essentially means non-polar, right? Remember, like dissolves like. Hydrophilic is the opposite. Water-loving. And because it likes water, what sort of things would like water? Well, water itself is polar. So something that would like water would also be polar. So if we have a structure given, we need to identify, in this case, the hydrophilic portions in red. All right, what would make something hydrophilic? Well, something that has a polar portion to it, and the nitrogen here being a highly electronegative element, will introduce some polarity. So we can highlight that. And that's the only thing we're added to, or we need to highlight here, the hydrophilic portion. If you decide that there aren't any hydrophilic portions, then you can just click on the thing down here on the bottom so we can check. And there we go. If instead this had asked me to identify hydrophobic, well, then the CH2s here and the CH3s, these would be hydrophobic portions, because anything with carbons and H's would be hydrophobic, right? So we'd have hydrophobic regions on the outside, the left side, the right side. The hydrophilic portion is where the nitrogen is. All right, so in the next one, we're looking at identifying isomers of a particular molecule. So if we're looking at constitutional isomers, remember now what this means is that we're going to be looking for things that have the same molecular formula. So that means that they're made up of the same number and types of atoms, but how those atoms are connected is going to be different, which leads to different structures. So for example, if we're given this molecule here on the left side to begin with, and again, I like to use a piece of scratch paper to work with initially. All right, so this, in addition to looking at isomers, this also will have you interpret these structures, make sure you're interpreting them properly. So we need to identify how many of the types of atoms that we have, right? So what do we have here? Well, we have a carbon at each of these locations, right? Wherever lines intersect, wherever lines meet, wherever lines begin, there's going to be a carbon. So we have a total of, let's see, 1, 2, 3, 4, 5, 6 carbons. And then, even though the H's are not shown, H's are assumed to be present in our structure. So how many H's are actually here? Well, we need to take a look at this and we can extend out our structure. So I'm going to draw in my carbons in green. And that way it might be a little bit easier to see how many H's. Remember, carbon likes to form 4 bonds, right? So if we start on the right side, this carbon here has 1 bond shown, so it needs 3 more to H's. That's a CH3. Same thing with the carbon here at the top. It's got 1 bond shown, so it needs 3 more H's to complete its octet. This carbon here has, and I'm going to highlight the bond here in orange, it's got 1, 2, 3, 4. So that carbon doesn't have any hydrogens attached to it. This carbon in purple right here has 1, 2, 3. So it needs 1 more bond to H. This carbon here has, let's see, it's got 1, 2, 3 bonds shown. So it needs a 4th one to an H. We'll draw that one in. And then the carbon at the end, it has, let's see, this one here has 1, 2 bonds. So it needs 2 more, and those are going to be to H's. All right, so all we need to do then is to count those H's. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all we need to do then is to look at the options given here. And we need to make sure that these structures have the same number and types of atoms. All right, so let's take a look at the first one. And we'll draw this down here on the bottom just to compare it. All right, so I have this structure. And same thing, I'm going to draw in my carbons. And I'm going to attach as many H's as possible to make sure that the carbons have a total of 4 bonds. So this carbon here on the right needs 2 more. This carbon here needs 2. This carbon here needs 2. This one on the left side needs 2 more. And then this carbon over here right now has 1, 2, 3 bonds. So it needs a 4th. And then the same thing for this carbon. It's got 1, 2, 3. So it needs a 4th bond. So we count those H's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 H's. How many carbons did we have? Well, we had 1, 2, 3, 4, 5, 6. Right? So we have the same formula, same molecular formula as this one here, but the structure is obviously different. So that would be a constitutional isomer. So that would be one of the options. Then you need to go through and identify any other ones that would be a constitutional isomer. All right, so in this one, we're looking again at structures, how we interpret, how we draw the different types of structures, because this is going to be a fairly big deal in organic chemistry. So it's really, really important that you're able to interpret and to draw the different types of structures. So mostly we're going to see the skeletal structures or the line angle structures, but sometimes you'll see the condensed structural formulas. So in this case, we're provided with a condensed structural formula, and we need to convert that to the line angle structure. All right. So if we look at our structure here, we have 1, 2, 3, 4, 5 carbons across the middle. So I can translate that to my line angle structure. I go 1, 2, 3, 4, 5 across the middle. And then the second to last carbon on the right, from the right side, has a carbon going up. That's this carbon here. And then I have an OH attached to it. All right, so if let me draw this out here so we can compare. Right, and we can draw in these arrows. So this carbon is that one at the end. This one here is the interior carbon. This is the other interior one. This CH is going to be this carbon here. The CH3 right there. The CH2 is going to be that. And then obviously now the OH is up here at the top. All right, so when we draw our structure, we're going to draw it like this. So it says to click and drag to start our structure drawing. So we go 1, 2, we extend it out, 1, 2, 3, 4, 5. All right, so I have my 1, 2, 3, 4, 5 across the middle. Over here, I need a carbon going up. And then going off to the left, I need an OH, right? So right at this end here, that's this OH. I'm going to put that in, and you need to make sure that that bond is connecting or is connected to the oxygen first and then the H, all right? So there should be some options here for what we want to put in, all right? So I'm just going to highlight this, click on it, and it says to edit the atom or the group. So if I put in just this OH, right, you may think, well, that maybe is correct, and let's check it. And you can see that it actually shows that it's wrong. And that's because the bond here that's shown, this bond in yellow, should actually be to the oxygen first and then the H. All right, so let's erase that. And we're going to draw in, you can actually type in, oops, erased it. So we're going to type in here an H and then the O, right? So you'll notice I have the HO. So the bond is actually to the oxygen and then the H that comes after it. If I check it now, this is in the correct form that ALEKS wants for these types of structures. So that's just a a minor thing, but if you find that it's if you're getting that error, most likely that's the issue, right? So the bond there is to the O, the OH, not OH in that order. All right, so we'll take a look at a little bit of the naming or the nomenclature for your alkanes, and this naming system kind of applies to all of our organic compounds. Okay, and it's a systematic way to name things, which means that once you get the system down, you can apply it to all types of molecules. So it's the IUPAC system, which is just a set of rules that we follow, and establishing the longest continuous carbon chain is the first part of this. So we need to know the prefixes that we use to assign the longest continuous carbon chain. So meth as a prefix means that there's one carbon, the longest chain. Eth is 2, prop is 3, bute is 4, pent is 5, hex is 6, hept is 7, oct is 8, non is 9, and then dec is 10. And we've seen several of these prefixes before with the covalent nomenclature, but there are a couple new ones that we'll need to know. So for example, if I take a look at this one here at the bottom, I have 1, 2, 3, 4, 5, 6, 7 all the way across. So the prefix for 7 there would be hept. And then this is an alkane because they're all carbon-carbon single bonds. So heptane would be the name for that one. So you want to go through and name these fairly simple alkanes using that system. All right, so the next one is sort of an extension of the naming and interpreting the structures. So when you name an organic compound, like these alkanes, some of them are going to be just one continuous chain. Others are going to have branches or substituent groups coming off of that main chain. But we still need to identify what the longest or the main chain is. And in this example, or in this problem, we're looking at tagging each carbon in the main chain. And it gives you the name of this compound. It's 2-methylbutane. Now, the thing about the name is that the last part of the name actually tells you the longest continuous carbon chain. So butane means that the longest continuous chain will have but, or 4 carbons in it. So I have the structure drawn here, and if I were to highlight the carbons in the longest chain, we can see that it's all the way across the middle. So 1, 2, 3, 4, and then we can see that there's a group or a branch hanging off of that, right? And if I wanted to number this chain, I would actually number from the right side, 1, 2, 3, 4, so that my substituent group is hanging off of the lowest numbered carbon, which in this case would be carbon number 2, hence the name 2-methyl. There's a methyl group coming off of carbon 2, and then butane, my longest continuous carbon chain. So if I tag or highlight, I can see that highlight these, and that's going to be the longest chain that I have. All right, so in this one, we're going to take a look at how we name these alkanes now that have maybe one or multiple branches attached to the longest carbon chain. So the same rule is going to apply. The first thing we need to do is to identify what the longest continuous carbon chain is. And in this case, I have this first structure drawn over here. And we can see that, and again, this is only going to come with practice. So you're going to have to do several of these to get fairly efficient at doing this. We can see that the longest carbon chain actually goes across the middle and then up. All right, so that's the longest unbroken or continuous carbon chain, regardless of bend. So when you look at the longest chain, it doesn't have to be in a straight line. It can zigzag or whatever, as long as it's continuous or unbroken. That's what we're looking for. All right. So if I look at the longest chain here, we can see that there's 1, 2, 3, 4, 5, 6. If I go from left to right, and if I go from left to right, we'll see there's a CH3 over here and a CH3 and another CH3. So I have 3 groups, 3 branches, and those branches are on carbon, would be on carbon 3. And these 2 here will be on carbon 5. Well, when you have a chain or a long chain, you have an option. You can number from one side or you can number from the other side. Well, is there a difference and does it matter? And the answer is yes, there is a difference and it does matter. So if I start numbering from the right side, this is carbon 1, that's 2, 3, 4, 5, and 6, right? So that's the green numbering system. And now I can see that my methyls here are on carbon 2, and then the third one is going to be on carbon 4. All right, so let's see the difference between them when it comes to naming. If I were to name this using the red numbering, my longest chain there is 6. So the last name for this would be hex, all carbon-carbon single bond, so hexane. I have a methyl on 3 and 2 more methyls on carbon 5. So I have a total of 3 methyls. So that would be trimethyl. We just attach it to the ending. And then I need to say where every single one of those methyls are attached. So one's on carbon 3, and I have 2 more. One's on carbon 5, and the other one is on carbon 5. So I separate them with a comma, and then when I have a number and a letter, I separate it with a dash or a hyphen. So this is named 3,5,5 trimethylhexane. Well, if I number it using the green numbering system, my longest chain is still 6. So it's still hexane. And I still have my 3 methyls, so it's still trimethyl. But now where they're located is different. Now I have 2 of them on carbon 2, so it's 2, 2. And then the third one is on carbon 4 over here. So 2, 2, and then 4 dash trimethylhexane. Now you'll see the ending here is the same for both of these, but the numbers at the front is different, right? So which one are we going to select? Well, we're going to select the one that gives the lowest numbers possible. And obviously 2, 2, 4, if you add these numbers together, you get 8. If you add the 3, 5, and 5 together, you get 13. So this one's going to be the correct name for this. So when you establish your longest chain, that's the first step. You want to choose the numbering system that'll give the lowest number possible to those substituent groups or to those branches that are hanging off of the longest chain. All right, so this one, as an example, we're looking at drawing the line structure of cyclobutane. Okay, and in organic chemistry, the name tells you a lot about what the structure is going to look like. So cyclo means that it's going to be a ring structure, and bute means 4 carbons, and the ane here tells you all carbon-carbon single bonds. Okay, so I need a ring made up of 4 carbons. So 1, 2, 3, 4. All carbon-to-carbon single bonds. Remember, there's a carbon wherever lines intersect. And in your line angle structure, you don't show your H's. H's are understood to be there. And that's it. If I were to draw this, okay, I attach it. Let's see. And there you go. It's a square. Is what cyclobutane is. All right, so in this one, we're going to be naming now organic compounds that have carbon-carbon multiple bonds. So alkanes are things that just have carbon-carbon single bonds. Alkenes have carbon-carbon double bonds, like the middle one here. And alkynes are going to have carbon-carbon triple bonds as the last one. So we're going to follow the same steps when it comes to the naming. We want to establish the longest continuous carbon chain, but when you have these multiple bonds, the longest continuous carbon chain has to include both carbons of the double or the triple bond. So in this case, the longest continuous carbon chain is going to be right across the middle. All right, so we have a total of, let's see, 1, 2, 3, 4 carbons, right? Across, that's the longest chain. So that would be a bute for 4 carbons of something. This here, that's a carbon-carbon double bond. That would mean that it's an alkene, which means then this would be named butene, would be the last name for this, right? So butene across the middle, right? This tells me, oh, takes care of that entire thing. Now, that's not the only thing we have. We also have this group here that's a methyl. And we need to say where this methyl group is attached, on which carbon is it attached to. So we then would need to, first of all, identify the numbering system for this. So we have a choice. We can go from left to right. We can go 1, 2, 3, 4, or we can go from right to left. We can go 1, 2, 3, 4. So in the case of alkenes and alkynes, you want to number the chain to give the lowest number possible to the carbon that starts the double or the triple bond. So if I go from left to right, I can see that the double bond here starts on carbon 2. So this would be 2-butene. If I go from right to left, going this way, the double bond still starts on carbon 2. So it's still going to be 2-butene, right? So either way, I get 2-butene. But then now I have to account for this methyl, right? And this is secondary. The primary thing that when it comes to the numbering is to give the lowest number possible to the carbon that starts the double or the triple bond. So in either case, 2 is going to be the lowest number. Now we need to give the lowest number possible to the methyl. Well, we can easily see that if I go from right to left, the methyl ends up being on carbon 3. So 3-methyl 2-butene. If I go from left to right, then the methyl is on carbon 2. So it becomes 2-methyl 2-butene. So obviously now this gives the lowest number. The 2 is the same in both cases. So this is going to win, right? So this will be called 2-methyl 2-butene. All right, so in this one, we're going in the opposite direction. Now we're given the name. So 2-methyl 1-propene. And now we want to draw the structure for this. And it says to draw the condensed structure of this. So again, I like to draw this on a separate piece of paper, and then you can translate it to the ALEKS template. So start with the last name. Okay, so 1-propene. Prop means 3 carbons. Ene means carbon-carbon double bond. And 1 here tells us that the double bond starts on carbon number 1. So if I draw just my line angle structure, I have 3 carbons, 1, 2, 3. Double bond starts on carbon 1 like this. And then I have 2-methyl. So I have a methyl group on carbon 2, like that. Right? This is going to be my line angle. If I need the condensed structure, so what do I have here? Well, I have a CH2, double bond to this here, that's a carbon. Connected to the top, I have a CH3, and then I have a CH3 on the right, right? And we'll color code these. Right here is my CH2. In the middle here, this carbon, let's do that in green. That's my carbon here. On the top, I have a CH3 that's going to be in red. Get red. And then on the right side, I'm going to have my CH3 at the end here in blue. All right, so when you draw your condensed structure, remember, it's not a line angle it's asking for, it's a condensed structure. So you want to include those H's as part of the formula. So if I want to translate this now to my ALEKS template, I'm going to draw my carbons first. All right, so oops, let's erase that. All right, so I have my first bond here on one side. I have a CH2, so I just clicked on this, and from the template, I select my CH2. Right here, I have a C, and then I have another bond. So there's a CH3 at the end. Let's find a CH3. That's that one. From the middle carbon, I have a CH3 going to the top. And I click on the end of it, add a CH3. Now I need a double bond between these two. So I click on the CH2 and drag it across to make it a double. So this now kind of looks like this. Let's check it and see if it looks correct. All right, so when you have carbon-carbon double bonds in a structure, the possibility exists for different types of isomerism to occur called cis-trans, or sometimes it's referred to as geometric isomerism. Okay, and in this type of isomerism, just like the previous type we looked at, you're going to have the same number and types of atoms. The connectivity is going to be the same. So the order of the atoms is going to be the same. But what's different is how the atoms are oriented, specifically around. So different orientation of the atoms around that double bond. And the reason is the carbon-carbon double bond does not rotate. It's not free to rotate like a single bond. So those atoms where they happen to be are locked in place. So how do we identify whether something can exist as a cis-trans isomer to begin with? Well, we want to establish, first of all, that there is a carbon-carbon double bond. And what we need to ensure is that the two remaining things attached to this carbon of the double bond need to be different, connected to two different things. Okay, and those can be individual atoms, they can be groups of atoms, doesn't matter. And the two remaining bonds to that carbon also need to be connected to two different things as well. Okay, so when we look at the structures given here on this, right, let's take a look maybe at the second one here. So there's my carbon-carbon double bond connected to this carbon. I have a Cl and I have another Cl. So right away, we know that that carbon is not connected to two different things. So this cannot be, or it won't be able to exist as a cis-trans. We don't even need to look at the other carbon because we've already established that this isn't connected to two different things. We can confirm also here that these two methyls are not different from each other either. So this cannot be cis-trans. If we take a look at this one, so there's a double bond. This carbon is connected to a methyl and it's connected to hydroxyl. So these are different, CH3 and an OH. So let's confirm that the carbon on the right is also connected to two different things. And we have a CH3 and we have an OH. So these two are different from each other as well. These two are different from each other. So yes, this can exist as cis-trans, right? So you want to, when you identify or try to identify the possibility for cis-trans isomerism, you find your double bond, carbon-carbon double bond, and you see at each carbon of the double bond, is the carbon connected to two different things? Is the one on the left connected to two different things? Is the one on the right connected to two different things? And if both of them are, then yes, they can exist as cis-trans isomers.